Question 6, the basicity question as part of aromatic or heteroaromatic compounds. Now, we went through part of this in our lectures, and this is just a way that we demonstrate something that we had already talked about. And that is, both of these are aromatic. One of them is basic and the other one is not. Now, I went through this in the lectures as part of explaining why it is pyridine is not anti-aromatic, as well as how it is pyrrole is aromatic. So, to remind you here, pyridine has a pi bond to the nitrogen already, along with a lone pair of electrons, which means in the simplest case, we'd be looking at its pi orbital overlaps with the rest of the ring as the aromatic system. So this is my aromatic overlap. The lone pair of electrons is in a different orbital, which means it can't participate in resonance. It has to be in an orbital that is orthogonal to those rings, to those other orbitals. So it's 90 degrees out. It is absolutely unable to be a part of things. As a result, pyridine is aromatic because the lone pair doesn't count for the 4n+2 rule. And since the lone pair is not part of making it aromatic, the lone pair can do stuff like pick up hydrogens as a base. So pyridine is basic and it's aromatic. Pyrrole, different problem. Here we don't have a pi bond to the nitrogen. If we freeze frame this somewhat incorrectly, but just for simplicity, we could say that nitrogen's sp3. It isn't because of resonance, but if resonance were removed from the picture, that nitrogen's sp3. So in this case, the hydrogen is going to be taking up the role of pointing out from the ring. The lone pair is part of resonance. So that lone pair is a part of making this aromatic in the first place. So it has to be considered as, now if we look at a resonance structure, well, now the nitrogen is not sp3. So we generally don't say that it is, but in freeze frame consideration of it, without drawing any resonance, okay, it looks like it's sp3. So the point here, though, is that for this to be aromatic, which it is, 6 pi electrons if I include the lone pair, the lone pair has to be a part of resonance, which means it's not available to do what I'm showing up here for pyridine. It's not available to go out and pick up a hydrogen. In fact, it's very, very unwilling to go out and pick up a hydrogen. And so that's the reason that we're seeing it be a terrible base. The pKa numbers that I showed you in the previous one, in the question, are just a way of demonstrating that. We could force it to be a base, it's just really bad at it. That conjugate acid is very strong, which means that equilibrium goes like this. There's not going to be any real trace of it going forward. It's a very unfavorable equilibrium in the forward direction. It's massively favorable in the reverse direction. So that's one way of looking at why that happens, or how demonstrating that the lone pair on pyrrole is required for aromaticity, is that we can't use it for what we would normally use a nitrogen for. That's why I had pyrrolidine up at first, which is the one without a double bond. So now aromaticity is not a question. So in this case, yes, it's very basic. So the pKa of the conjugate base there is like 11 and change. I had to cut that off to make the cut and paste of the question fit on this page, but the point is that one is obviously basic. Pyridine a little bit less so because the nitrogen is sp2, and pyrrole not at all. The next part of it is saying draw Frost diagrams. So this is partially helpful and partially not. So if I draw those for pyridine, so I'm drawing the ring inside a circle, and those are my orbitals, and the non-bonding goes down the middle of that. That I'll have electrons in the bonding ones, 3 separate bonding orbitals, all of which are there, no problem. And if I look at, this is pyridine, so it doesn't really matter which atom I put where there, but this is just a graphic to help you set up where the orbital energy levels are. If I do that here, as far as the pi orbitals, they haven't changed. So essentially, I'm drawing the same diagram. My point is, the lone pair has no effect on aromaticity for nitrogen, for no effect on the aromaticity of pyridine. If I do that for pyrrole, though, it's a little different. If I say, all right, well, this is a 5-membered ring, so it's not as direct in terms of where the center point is. It still has degeneracy, so I still have 2 equal orbitals. Pyrrole, the non-protonated version, which I'll draw in a second, looks like this. So very similar. So this is the non-protonated version. Realistically, a Frost diagram is not really perfect for the other case because it's not aromatic anymore. Frost diagrams are to help us with aromatic rings. Well, so that part of the premise of the question is a little awkward, but the point is, for it to be aromatic, I need 6 pi electrons in those 3 bonding orbitals, and I'm not going to have that. So what I'm going to have instead, if it's protonated, is this. Essentially, if I'm looking at it being protonated, this is just a diene. At which point we're looking at orbitals like the ones in the previous Diels-Alder question, where there's going to be 4 orbitals involved and there's not going to be a cyclic to it, because there's no cyclic conjugation once this is protonated. It disrupts the aromaticity. So it's not exactly ideal. If you had drawn it with just, one of those gone with only 4 electrons there, or if you somewhat more properly had sort of split them like that and had, 2 here, that's fine. It wasn't ideal. It was just to make you remember how to draw Frost diagrams and to show you, at least for pyridine, there's no difference whether it's protonated or not. It's still got 6 pi bonding electrons no matter what we do to that nitrogen lone pair. That is not the case for pyrrole. So the Frost diagram on that last example, the protonated pyrrole, really wasn't ideal, but I didn't count off for it if you drew it oddly, because there's no correct way to draw it with a Frost diagram. Everyone makes mistakes, including people who've done this way too long. So, but my point was to show you that at least for pyridine, the top case doesn't make any difference. The Frost diagram for the protonated version is exactly the same, because the electrons involved in that protonation have nothing to do with the aromaticity system.